So hopefully everything will be okay. Recording. Okay, now let's restart. Okay, why do we need probability at first place? Okay, actually, okay, of course, from the statement over here, we know that to make probability statements about the significance on our statistics. And then what is statistics? Statistics basically is the things that you actually, you want when you're collecting data, okay, when you're collecting a stats of raw data, okay, you basically want to make sense of it, or else a bunch of 1, 1, 2, 2, 3, 3, or 10, or hundreds and so on doesn't give you any meaning at all. That's the reason why in your secondary class, I would say, you are actually learning mean, mode, median, and so on to actually represent your information in a collective manner rather than the raw data standalone. Okay, but why probability over here is important? You can imagine a situation like a dice roll or a coin toss, maybe a dice roll. We know that a dice roll in general, we have fair dice, we actually put in the probability over 1/6. Okay. Is everyone hearing clearly? Okay, right? So far so good, right? Okay.
Yeah, all good, all good.
Yes.
Because I'm receiving limited response. Anyway, okay. So what this probability 1/6 tells you in a dice or in a fair dice roll? It basically tells you that okay, in a roll, every single 1, 2, 3, 4, 5, 6 outcomes, okay, in the dice, okay, have an equal probability. That's why for you to get 1 is 1/6, for you to get 2 is 1/6, for you to get 3 is 1/6, and so on. Okay, but okay, let me maybe come on, I actually put in noise, right? Come on. So when you have actually 1/6, okay, 1/6 over here, this is actually for dice roll. I want to draw something, come on. It's actually for dice roll, okay? But when you're doing a dice roll about like 6 times, okay, you're expecting that all the 6 outcomes will be like 1, 3, 2, 5, 4, 6, and so on, right? And then you repeat basically 1, 3, 2, 5, 4, 6, or 6, 4, 1, 3, because in the end of the day, you're expecting that the probability for it to come out supposed to have certain kind of patterns like this. Okay, for example, in the first 6 block, right? If 1 is already happened, it will not happen again for the next 5. It will also happen 3, happen 2, and happen 5, and so on. Okay, but is it really true? Sometimes in statistics, right, whenever you are doing your data collections on your dice roll, for example, you don't really have 1, 2, 4, and then maybe 4, 5, 6, 2, 1, 2, and so on. You're collecting this kind of data. So in that case, if you are calculating your probability and so on at one stepping point, like for example, you're calculating from here, is it trying to tell you that this dice basically is not a fair dice? It's not so, okay? Because if you're just calculating based on this tree, probably for 1 to happen is 1/3. Probably 2 will happen is 1/3. Probably 4 to happen is 1/3. But the rest of the information is actually it will not happen at all. 3, 5, and 6 will not happen at all. Probably it's 0. But it's not so. Okay, it's actually not so because why? This probably basically tells you a general concept or general tendency on your dice roll supposed to behave. Okay, so whenever you are actually getting more and more information, now you know that roughly this one is actually getting 1/6, 1/6, 1/6, 1/6. This one is getting 2/6. Okay, for rolling of 4, and then 3 gone. Is it normal? It's actually normal in a general environment, or we call it in a real life environment. Because why? It's whenever our dice roll is actually every single our dice roll is actually independent. Okay, so you are actually it's not dependent on the previous case that you have. Okay, but in terms of probability, we are trying to give you a general concept. In general, when you're performing the dice roll, it will behave in this way. Okay, so it's actually quite different from statistics. Probability basically when you are actually given this kind of information, okay, given this kind of information, you try to describe, okay, what kind of potential outcome that you actually have. Statistics is another way around. Whenever you have collected this kind of data, what kind of probability distribution is actually supposed to show or behave. Okay, so one is actually based on data driven. One is actually based on concept driven, or it's actually again based on much bigger data. Okay, that's the reason why later on when you are doing your statistical analysis, you actually have a sample mean and also a population mean. Yeah, of course, the concept is a bit different, but basically there are a small sets of data and also a large set of data for you to check on. Okay, so never mind, that one we'll actually cover later on. But in short, what I wanted to tell you over here right now is probability basically tries to give you a general idea how the events, how the outcome is supposed to be behaving after certain kind of events or action that you actually perform. Okay, but the example over here, what this example actually means. Let's just see this example. Yeah. For WIA 203, mean height is actually 66.7 inches. So what is the chances that the true height of FSKDM student is between 60 to 70? For this one, 60 to 70 is actually quite possible because your mean is actually fall between 60 to 70. But is this the only information that you actually can get? Let's check on this one, okay? You doesn't know for sure. Because why? You're actually having a very limited information where you just know, okay, your mean is actually 66.7. You don't really know your standard deviation and so how it deviates. Or you're having this information in terms of how far your data is, to have outliers and so on. You doesn't know that. But, okay, what you can tell from the 66.4 inches over here is when you are comparing with another set of means, you have a higher chance or a lower chance to actually get your data to be between 60 to 70 inches. For example, if you are comparing 66.7 inches, a set of data with 66.7 inches, and another set of data with 75 inches, okay? And you're asking the questions, 60 to 70, which one is having higher chance? Then, of course, based on your general understanding, 66.7 inches is actually having higher chance because your mean is basically fall into your range between 60 to 70. But of course, there are some limitation on the mean as well, as you are aware. If your data is really scattered, like your data is actually 10, 20, and then you have 100 and then 110, then your mean is still 66.7, but you are having a very low chance to get true high or FSKDM students between 60 to 70. So this is actually your so-called statistics, okay? And then it's actually giving you some measurement on the understanding, okay? The understanding on your data. But the probability basically tries to tell you how probable this actually happens for this kind of particular questions that you actually raise in. Okay, so this is basically how you can actually understand what the probability can do. The next one, same case, R equals to negative 0.22 for cash withdrawal and birthday. So these two is actually two different variables. We are using the word as variables, and then R basically over here is actually your correlation coefficients. Okay, so what's the chance that the true correlation is significantly different from 0? When you're actually having a significant difference from, your correlation is 0 correlation, right? Your correlation is supposed to look like this. Okay, so your X and Y, right? For example, your X and Y, you are actually having X and Y over here. Whatever your X changes, okay, whatever X changes, your Y doesn't change at all. Okay, so your your correlation basically is 0 correlation because it doesn't correlate at all. Nothing change when X change. Well, nothing from Y change when X change. Okay, but in that case, R equals to negative 0.22. How does it tell us that what is the chance that the true correlation is significantly different from 0? Again, you don't really have things to compare, right? You won't be able to tell the answer. So in that case, it doesn't know for sure again. But R equals to negative 0.22 have a lower chance that R equals to negative 0.05. Why? Because negative 0.05 is closer to 0. And 0 basically, oh my God. 0 is basically correlation, okay? Doesn't know for sure, sorry. Let's see. Yeah, okay. So 0 basically is actually true correlation, 0 correlation. That's why when you're comparing 0 and 2, so Hey, come on. 0.22 is actually your 0.22 is actually having a higher probability, okay, for you to get. 0.22 is actually having a lower chances for you to get zero correlation, okay, compared to 0.05. You always have two sets to compare, okay. Okay, and then I'm not sure why my notifications keep coming out, but it's actually something else that I actually don't want to come out right now. So anyway, let's continue. In deterministic process, this one is basically in general understanding what the probability looks like, okay? And then in deterministic process, the outcome can be predicted exactly in advance, okay? And then in random process, the outcome is not known exactly. So in these two terminology, basically it's trying to tell you a definite outcome and also a random outcome. And random outcome is the one that we actually learn for the probability distribution over here, okay? Because why? Only in random processes we are able to measure probability. If it's in the deterministic process, no matter how many times you are executing your calculations, okay, you're always getting the same answer, F equals to MA, okay, F equals to MA. And for example, I mean, MA equals to F. This one is actually a force equals to mass times acceleration. It's actually a fixed formula. Of course, we didn't take into account other kind of variables or information as well. But in this particular formula, basically this one we're understanding deterministic process. Your left hand side and right hand side is basically vice versa. You can go left and right actually. And random processes is whenever you are executing the events or performing certain kind of actions, basically your outcome can be different. Your outcome sometimes in your dice roll, for example, can be 1, can be 3, can be 5, and so on. Come on. Okay. And then you also have that's why you need to have a probability distribution for you to cover up all this kind of possible outcome. Okay. That's the reason why probability is needed over here to cater or to represent the random process that we actually have. Oh my God. Okay. Okay, before I joining in about events, right? Can we take 5 minutes break? I will need to disable all my notifications somehow. Okay. I'll come back in around 5 minutes. So take a look on the events part first. Okay. Thank you. I'll come back very soon. It's quite annoying, right? It's okay to have the Teams notification, but I'm not sure why the other notification noises is keep coming in, because I need to keep the Telegram over here. Oh, come on. Okay, give me some time, yeah? Thank you. We'll stop the recording for a while. It's still coming in, so I try my best to reduce it, but hopefully it'll be okay, much better this time. Unfortunately, this iPad is I'm not the only one using it. So anyway, let's continue. Okay. Okay, an event. Is everyone okay? Sorry, 5 minutes, right? Okay, I believe so. 5 minutes. Okay, event is an outcome or a set of outcomes of a random process. So what this events basically tells you. Okay, if you are doing programming, then you know that there are click event, touch event, and so on, right? So you notice that this event is triggered by something. You actually perform some actions, you have done something, okay? In general, we are saying that done something, and you basically change the environment, or you actually have certain kind of outcome after you have done something. That's the reason why we are considering this kind as a event, okay? For example, over here, you actually have tossing a coin 3 times, okay? So in general, we know that tossing a coin 3 times, you're actually having an outcome of heads and and also tails. Okay, heads and tails, and actually the potential outcome they actually get from the coins. Okay, of course it's a fair coins, and then you actually have 3 times. Okay, this 3 times, right, is actually trying to tell you that you can have. Okay, you can have hedge. Okay, 3 heads. or tail, 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 or H, H, T, H, T, H, and so on. And as you know, if you write all the possibilities, or all the possibilities, you're actually having 8 possibilities. Okay? But, okay, event over here is basically trying to tell you a special kind of outcome. Okay, I wouldn't say a specific, but maybe the word special is also not so good enough, but it's actually a very constraint, okay? Or you're given a set of rules, okay? You're given a set of rules, and then you're expecting that what are the potential outcome from there, okay? Rather than you're always writing the all 8 outcomes. So you're actually trying to get a subset of it. And this subset of it following certain kind of rules. That's the reason why it's considering as an event. And this event is always defined in a certain kind of way where, like for example, over here, getting exactly 2 heads. So you know that you have 1 head over here. Sorry. You have 1 head over here, 2 head over here. 1 head over here, 2 head over here. 1 head over here, 2 head over here. That's the reason why these 3 specific outcome, okay, is actually a subset of these total 8 outcomes. Subset, okay? Subset, okay? And then this one is 3 heads, right? So this one this 3 heads is not counted, 3 tails is not counted, and so on. So you are trying to find out what are the potential outcome over here that fit these requirements. Okay, so it can be requirements as well. So there are many ways to tell it, but in probability understanding, we always call this as an event. Okay. So picking real number x between 1 to 20. Okay. And the event A is a chosen number is at most 8.23. Okay. So you notice that this is actually the action. You are trying to pick the value between 1 to 20, and then you want to find the probability for event A to happen. Okay, the probability for event A to happen over here is actually, you need to measure in this way. Your x is smaller or equals to 8.23. Why is it the equal sign is included? At most. So this one is actually also one of the important element in the probability where you need to understand the choice of word that you are using carefully. Okay, because at most over here, basically you include the equal sign. Okay, if you are using the word less than, then the equal sign is not supposed to be included. Okay, so this kind of words, you need to be careful as well. Then the third one, tossing a fair dice. Okay, tossing a fair dice. So you know that in general, you know that the probability is 1/6. Okay, for every single potential outcome, and the outcome that you have will be definitely 1, 2, 3, 4, 5, 6. Because fair dice, you can actually make it unfair easily by changing, like for example, the outcome. You can change 1 to 2. Then your probability for 1 to happen is gone, and probably for 2 to happen basically double up. So this is how the unfair dice is actually created. But when you are seeing a fair dice, basically you need to know it's in general this way. Okay. And then event A, result is an even number. So when you're capturing even number, 2, 4, 6. Okay, so this one is clear. So notation over here, probability for A to happen. Okay, probability for event A, probability for an event to happen. Okay, so there are many ways for you to tell, but in general, we will actually write in this way. PA. Okay, so probability for A, and A is equals to this one. So that's why I always ask students when you are doing your questions, when you're answering your questions later on your quiz or your exam and so on. Whenever you're writing probability of A times probability of B equals to something else, okay, you must define what is A, what is B from the question that you have. You must tell what is the event that you're measuring, okay, or else the marker will not know what you're talking about, all right? And of course, one and most important probability rule that you must recall is the probability rule: 0 smaller than your probability, smaller than 1, because the total probability that you count off together, you sum up together, cannot be more than 1. Okay. The total must be equals to 1. So that's why for every single element that the event that you're measuring is actually must be smaller than 1. Okay. So in general, if I'm writing a probability for all these all these events to happen in your potential outcomes, then of course the probability is actually 1, because all these events is actually cover up all the potential possibilities, right? So your probability is 1. But if you are just measuring the event itself, just the subset 1, 2, 3, and your total outcome is actually 8, so your probability will become 3/8. Like for example, this one will be 3/8. This one will be maybe 1. Okay, maybe you want to do 8.23 minus 1 divided by 20. Okay, and then the last one, because its range is 1 to 20, it's not 0 to 20. You need to be careful somehow. And then the last one, fair dice, 2, 4, 6, and then all your dice outcome is actually 1, 2, 3, 4, 5, 6. So this one is 1/2. Okay, so this is the thing that you need to be careful. Okay, sample space. So just now, I'm just trying to tell you this one is actually all your potential outcomes, right? So all the potential outcome have a fixed name, okay? It's actually called sample space, okay? So the sample space is a random process which covers the sets of all possible outcomes. For example, over here, 1 coin toss, you have 1 head or 1 tail. If you have 3 coin toss, head, you have 8 outcomes, like what I'm actually drawing over here. And then you have roll a 6-sided dice. You have 1, 2, 3, 4, 5, 6, and then pick a real number between x and over 20. So all real numbers between 1 to 20. So probability rule 2 that is the one that I actually tried to tell you just now. The probability for the whole sample space is 1. Okay, so basically just now I already covered these two: probability rule 1 and probability rule 2. In terms of notation wise, the probability of event A is represented by PA. So this one is exactly the same. So you have if probability is equal to 0, then event is almost definitely not occur. If close to 0, a small chance. 0.5, 50-50 chance. 0.9, a very strong chance. Equals to 1, almost definitely occur. Because in probability,
So I guess we lost Dr. Ho. So just let's wait for him. I think the line cut or something. I'm not sure. It's a bit, network is a bit unstable.
did I disconnect?
Yes, we are back now.
Come on.
Okay.
Oh my God. How many slides did we miss? Are we still here? Are we still here?
Yes, we can hear you.
No.
But we can't see the slides.
The pre-PA probability.
Let me see. Come on. I really, sometimes at one point I really hate this. I not even know that I have disconnected. Come on. Okay, recording. Okay, recording is continued. Okay. Luckily, there are some noises coming from my phone, so I'm like, huh? Okay. So is this done?
Yes.
This is done. This one? This one?
Yes.
This one is done, right? Then it's good. Okay, just disconnected. Okay, good.
Yeah.
Okay, so this one, we come back to this. Okay. All right. Let me go forward. Okay, good. So this probability, we actually have because the range is actually between 0 to 1. So 0 and the values between 0 to 1 actually gives you different kind of meanings. So that's the reason why when you're getting probability of A equals to 0, it's almost definitely not happen. If it's close to 1, there's a small chance to happen. Equals to 0.5, you have a 50% chance. Somebody might need to mute the noise. Okay. And then probability of A equals to 0. Ouch. Where's the noise coming from? Okay, hopefully okay now. And then the last one, probability of A equals to 1, then the event A will almost definitely occur. So basically, this range of values give you certain kind of meanings over there. But there's one but over here is because probability is always calculated or measured based on sample mean or sample information, okay? Sample data that you actually collected from the population that you actually have, okay? That's the reason why even though your probability that you actually calculated is 0 or 1, okay, if it's 0 or 1, it still don't give you definite answer. It will always give you a certain kind of almost definite, or sorry, almost definitely not occur or almost definitely occur, because based on your data collection or based on your research or calculation or understanding on the project or on the data that you have, you deduce that okay, 0 probability or 1 probability is equals to 1 definitely occur. But because of the data that we're actually assuming is actually just a sample set of data, that's the reason why the choice of words over here, we can't say the word definite exactly, okay? So this one, if you are interested, right, if you are, maybe you are from AI, okay? Maybe later on when you are studying in fuzzy logics, then you can compare the difference between this one and fuzzy logic, okay? So these two concepts, right, are also 0 to 1. But the conceptual understanding over here is quite different, okay? So, but if you're interested, please go into look into the different concept between probability and fuzzy logic, okay? And then, okay, we continue. The sum of all possible outcomes in the statistical experiment is equals to 1. So this one is actually repeating this one, okay? Everything when you sum together is supposed to be equals to 1 because you are capturing all the sample space outcome, okay? Sorry. And then this means that if an experiment have 3 possible outcomes, then probability of A plus probability of B plus probability of C equals to 1, okay? And then the probability of S, okay, of over here is, sometimes I don't want to use S again, but because making you a bit confused, but okay. Number of successful outcomes divided by total number of equally likely outcomes equals to R divided by N over here, okay? So this one basically tries to tell you that, again, we go back to the example. Like this one, we have 1, 2, 3 successful outcomes, okay? So this one belongs to R, okay, for the coin toss. But equally probable outcome is actually this one, sample data from a sample space. 1, 2, 3, 4, 5, 6, 7, 8. So you got total number of equal likely outcomes, 8. That's why probability for your getting exactly 2 heads, okay, is actually equals to 3 over 8. So this is how it comes from. Okay, so this is an example. An urn have 10 marbles, 2 marbles are red, 3 are green, 5 are blue. So if an experimenter randomly selects a marble from a urn from the urn, so what's the probability that it will be actually green? So of course, you should spend some time to attempt this, okay? So, but right now we are actually sharing the answer directly because I think I just uploaded like half an hour before the class. So next round I will be uploading a bit earlier, so please attend it before the class here if you're having time. So in this experiment, there are 10 equally likely outcomes, 3 of which are green marbles, okay? So you have 2 red, okay, let me draw it, write it down. You have, wait, 2 red, 3 green, and then 5 blue. And then you total up, become 10. Okay? Randomly select 1 marble from the, what's the probability that it will be green? You are looking at this green over here. Your total sample space is actually 10. Okay? That's why based on the equation that you actually have over here, you become 3 over 10. Because 3 comes from here, your 10 comes from here. Okay? 10 is your sample space because you have 5 plus 3 plus 2, and then you have 3 over here as your successful outcome as green marbles. Okay. Then, when the order is taken, okay, this one, sample space, how you calculate sample space in events. Because why? Sometimes when your problem is getting more and more complicated, okay, not just that simple, you are getting 3 and 10 like this, then you need to have some ways to calculate your you calculate the events or the sample space that you actually have. So in that case, you can use permutations and combinations. Okay, what's wrong? Okay, fine. So a permutation and combinations, again, is actually something that you have learned before, but in general, we're gonna cover a bit again, which is permutation is actually an ordered combinations, all right? And then the equations is follows, where you actually can calculate different permutations and also with and without repetition, and also combination with and without repetitions, right? So, for example, over like this one, given a travel log, there are 3 numbers to set from choices from 0 to 9. So what are the possible orders to set? Again, before you go into the answer, I will always suggest you try yourself first. If you are stuck, then you know where you're stuck, then you know why this is actually your answer. All right. Because why? Travel log over here have 3 numbers to set from choices 0 to 9. And whenever you are setting your log, okay, like this one, right? This, sorry. Come on. This one, this one, and this one, and this one. It's not linked. It's not linked. Hey, oh, I didn't put 1 to 9, I put 0 to 9. Yeah, you are correct actually. It's 10,000 to the power of 3. Yes, you are correct, you see? That's a good thing about we have actually a video call right now. Because why? Whenever I'm delivering a lecture, no one will actually correct me. Right now, I'm good. I can see some answer over here. It's actually 10. 10. Okay? Because 1 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you actually have 10 outcomes. Okay, and then you have 3 sets of number, 3 sets, and then this one is 10, this one is 10, this one is 10. That's why you're actually getting 10 to the power of 3 equals to 10,000. Okay, good for correcting me. So I'm gonna update the slides later. Then, in the pool game, there will be a total of 16 different pool balls. Now, yeah, I totally happy that you're actually correcting us, because when we are actually creating a site, right, there are many information you need to cater into front and back. So it's easy for us to actually make mistakes like those, for example, this one. And even when you're correcting us, we see that it's actually true, then we are actually very happy. Thank you for that. Okay. So 16 different pool balls. What are the total possible orders for the first 3 pool balls are in? This one? This one is actually without repetition. Because why? What's the difference between with repetition and without repetition over here? Repetition means that whenever you are having picked the first one, you can pick 0 to 9. For the second pick, you can also pick 0 to 9. For the third pick, you also can pick 0 to 9. Okay? But for without repetition, the first pick, if you are picking in, like for example, over here, 1 over 16. If you, for example, pick the 16, right? Then the next pick, this is the first one, second one. Then you can only pick 1 to 15. Okay? Then if your second pick is actually picking 3, then your third pick can only pick 1 to 2 and then 4 to 15 and so on. Basically your environment or your potential outcome is actually reducing over time. That's why your potential permutation is basically reducing as well. Okay, that's the reason why you can't use the same formula n to the power of r anymore, where you need to use this kind of formula this time. And whenever you know that n is your 60, your total balls, and r is actually the ball that you want to pick, then you can apply your formula and you get your answer. Okay. The third one, combination without repetition. Okay. So this time it's actually different, yeah. Combination, yeah. It's not the permutation anymore. Okay, you notice that permutation is actually reducing. Why? Permutation is actually reducing comparing to, combination outcome. Combination outcome is actually reducing compared to your permutation outcome. Why? Because the order is no longer important. Maybe I try to write this one as well. Maybe I put 6 over here. Because from this one, we're actually having the information. We are picking 16, and then we are picking 3, and then we are picking 6. Okay, and so on. But if we stop at 3, right? So we don't really have a so on anymore. But if we are actually picking 3, 6, and then 16, In permutation wise, these two are considered two different outcomes. This outcome one, this is outcome two. Outcome two. This outcome one, outcome two. But for combination wise, this kind of order, okay, this kind of order, 16, 3, 6, and 16, 3, 6, wait. 16, 3, 6, okay, and 3, 6, 16, okay. For them, it's the same. In terms of combination wise, that's why it's actually reduced. Your outcome, your potential outcome is actually reduced because you are reducing the somehow in combination we consider it as duplicates. Okay, because even though the sequence is actually different, 16, 3, okay, sorry, 16, 3, 6, and 3, 6, 16, it's still considering, if you rearranging it, it's actually still 3, 6, 16 as your outcome, if you rearrange it, okay? So this is what we understand as combinations, comparing with permutations. And then the last one, you even have a combination with repetition. What does this mean? Given that there are 5 choices of ice cream flavor, how many combinations are there if we can have 3 scoops? Okay. What's the answer? Why the answer is looking like this? Because this one is actually the one that is actually having most confusion. Whenever you're actually performing a combination calculation with repetitions, right, means that whenever you're actually getting the the red flavor, you can get another red flavor again. Okay, that's why you're actually getting a repetition over here. Okay, but you want to have 3 scopes. Okay, you want to have 3 scopes. Yeah. So how are you able to actually try to find out? Okay, find out the differences. Sorry, not the differences. The potential outcome when repetition is actually allowed this time. Because usually, if you are using without repetition over here, once you pick 16, you can't take 16 again. But this one is, once you pick red, you can pick red again. Once you pick red, and also you actually have other potential possibility, red and then white, and then red and then another one scopes, okay? So the formula is given like this. But I understand that if I just explaining in this way, okay, in terms of the slides, some of you might have issues of understanding it. So later on, you try to find some online material, okay? And then I will also release one extra notes, okay, just for this one, because it's very hard for me to explain it directly from here, from these slides only. So I will actually release an extra note to explain this one. But please go and find out, so what's the difference between this one and this one? All right, because for some students, you have difficulties on understanding this part, okay? So this one is one of the take-home work, yeah? Then you have probability definitions. I already explained to you 3, so you have 1 more for you to check on. But of course, I will tell you next week. Okay, the probability that event A and B both occur is actually probability of intersections A and B. So whenever you actually have probability definitions, right, it's actually very similar to the sets that you have learned before. Okay, like for example, over here, you have A and B. A and B is intersection. Intersection looks like this, almost the same with your set. Okay, and then for union, it's A or B. You have union A or B, and you have a sign like this. And now continue. We actually have conditional probability for you to have event A and event B. You already know the event B is happening. Okay, it's already happened. And what's the probability for A to happen as after you confirm that probably B is happening? It's actually very different from A intersect B. Yeah, A intersect B is, and A given B is different. A intersect B is A and B happen together. Okay? Have the chances of A and B happen together is this one. The chances of A happen, okay? You're measuring actually A happen, but you are changing your environment calculations, right, to a situation where you already know that B is happening. That's why you are using the word conditional probability over here. The condition over here is trying to tell you that, okay, B is already happening. So we can forget about the rest of the data that you actually have, okay? But once you already know that B is actually happening, what's the probability for A to happen? All right. So, so this one, if you are confused, please try the tutorial questions, the last questions, okay, later on when we are showing, okay? So from that question, you're supposed to be able to differentiate between this one and this one. Intersection and conditional probability, right? It's on a new sample space. It's no longer the sample space that you have ordinary, all right? Then you also have dependent and independent. If the occurrence of events A change the probability of event B, then the A and B are dependent. On the other hand, if the occurrence of A does not change, okay, one does change. Okay, where is it? Change. One change, one does not change. All right. So if it does not change, it will become independent. All right. So what does this mean? It means that whenever your A changes, whatever A changes doesn't change the potential outcome of event B. Similar to this one. Okay. Of course, this one we are not measuring probability, but your event A, okay, doesn't change the probability of event B. All right. This one not a probability question, it's a permutation, but you can actually explain that particular concept in this way. This one, your event A change the outcome of event B. All right. Let me see. Let's go back over here. Yeah, yes. And then complement. And then there's also a function, not a formula. Okay. Usually, if you are applying a conditional probability formula, right? Conditional probability formula, probability of A given B, okay? Probability A given B, if it's independent on these particular two events, probability of A given B will be equal to probability of A, because even though you know that B is happening, it doesn't affect the probability of A to happen at all. So in that case, this is what we understand as independence, right? Then the complement of events is other events that are not occurring. So for example, just now we actually have 3/8, right? Sorry, the getting exactly 2 heads is actually 3/8. So your complement is the rest of it will become 5/8 because it's 1 minus. Okay, you get what I mean? So yeah, so you know, okay. Then continue. Rule of subtraction, rule of multiplication, rule of addition. So if you have gone through 1, 2, 3 slides and you are still having questions on this one, okay? Did I mention about mutual exclusive? Okay. Where is the slide on mutual exclusive? It seems gone. Okay. Why? Let me double check on the slide later on. You're supposed to have mutual exclusive as well. Never mind, I will double check the slides here, but you're supposed to be getting all the information over here. Okay, and then rule of subtraction, rule of multiplication, and also rule of addition. Okay. Rule of subtraction basically over here is trying to tell you, it's actually equivalent to your complement concept. Probability of A equals to 1 minus probability of A complement. Okay, it's actually similar to this one. So, for example, the probability for Bill will graduate from college 0.8. So the probability for Bill will not graduate basically is 1 minus 0.8 equals to 0.2. The rule of multiplication applies to the situation when we want to know the probability of the intersection of the two events. Why? Maybe because the other class has finished. Okay, never mind. Okay, that is, we want to we take 3 minutes break because there's many noise right now for me. Just 3 minutes break, yeah. So this is the bad thing about having a multiple sessions. I need to take out later. Okay. So rules of multiplications. We take 2 minutes break. We continue at 10:30. Okay, very fast. I just want all the message to go off. I think I better withdraw myself from there. Okay, we continue. The rules of multiplication basically applies to the situation where we want to know the probability of the intersection. So just now we already know the intersection, right? It's probably A given B. Probability of A intersect with B. So it's a NB, okay? NB. So in that case, we want to know the probability of the two events both occur. So in that case, we need to times them together in this kind of situation. But if you notice just now, we actually have independence cases, right? So if it's independent, it will actually become probability of A times probability of B, because A is not important. I mean, A doesn't affect B at this point if it's independent. Okay, the example over here. An urn contains 6 marbles and 4 black marbles. 2 marbles are drawn without replacement from the urn. So what's the probability that both of the marbles are black? Okay, both of the marbles are black. Yeah, you are actually drawing, 2 marbles over here. Yeah, and then the important thing over here is without replacement. What do we understand by without replacement? So whenever we're actually having an urn like this over here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Without replacement basically tries to tell you, once you take out 1 marble, you don't put it back, you take another marble again. All right? But there's a situation where there's a with replacement as well. So if you have the same urn, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. All right? If you take with replacement, right, once you take your marble, wrong direction. If you take a marble out, you put back the marble and you pick another marble again. So the difference between these two over here is if it's without replacement, it's actually dependent. Okay, because your first event is actually affecting your second event in terms of number of marbles inside your urn. Okay, but if it's with replacement, it's actually independent. Why? Why is it independent? This is because whenever you're actually taking out the marble, you put it back. Once you put it back, the number of marbles inside is always the same. Okay, it's always the same. So in that case, since your data or the number of urns inside is always the same, your environment doesn't change. That's the reason why in the end of the day it's actually considered independent. All right. So this is actually you need to be careful in terms of how to identify the event to be independent or not. All right. Like for example, all the coin toss supposed to be independent because the first toss and the second toss is not supposed to be affecting each other. Or every single dice roll is not supposed to be affecting each other as well. Okay. Unless there are certain kind of rules telling you that it's actually dependent. Okay. So the example over here, you are actually doing without replacement, right? So it's dependent event. The first one is 4/10. Why? Because there are 10 marbles in the urn, 4 of them is actually black, so 4/10. After the first selection, you just have 9 marbles, so you can see a difference right now. And then 3 of which are black, so you are actually getting 3/9. So probably for this one is actually probability of A. For this one is probably B given A. This is how you are able to tell B given A is actually this, because of the changes of the environment in terms of number of marbles inside. Okay. Rules of additions. So this one is actually we want to know the probability that either event occurs. I didn't put the answer. Okay. So this one, probability of union. If you still recall your sets, right? If this one is A, this one is B. Okay, you want to get the union. So for you, you can actually simply add probability of A and probability of B, right? So you will get 1A. You get the A and you get the B as well. But you also notice that this center part is added twice. That's the reason why you need to cover up by using the minusing the intersection over here, because you just want to calculate this whole part of it once only. Okay, so if you are adding in probability of A plus probability of B minus this one, then you are getting the full union of the outcome. So the students go to the library, the probability of she checks out. A word of fiction is 0.4. A word of non-fiction is 0.3. Both fictions and non-fiction is 0.2. So what's the probability for you to check out the word of fiction, non-fiction, or both? So I hope you know the answer. I really hope that you know the answer for this one after explaining this one, because I think I forgot to put in the answer slide. So this is a very, very, very simple take-home task. Second take-home task somehow. Yes. Okay. Yes. So, and then you have a discrete random variable, continuous random variable. So you actually see that there are different kind of sections over here. All right. Random variables. So when the numerical of a variable is actually determined by the chance event, that variable is called a random variable. So what the things that we are actually discussing just now is basically all random variables. Most of them, because all your outcome is actually keep changing. And that is governed by the probability events that we actually calculated. Okay, so we don't know for sure which number we actually observe when the experiment is performed. Like for example, when you are tossing the coin, okay, or you're rolling the dice, or maybe rolling the dice, okay, you don't know that your next outcome is actually 1 or 3 or 5 and so on. So whenever you are not you're unsure about the outcome, the variable that you are actually using to govern the outcome basically is a random variable. Okay. Okay. Random variable x is a function from a sample space S into the real numbers. Okay. So in the different number, value of x is typically observed on each trial of the experiment, therefore known as variable. Because why? You're actually observing data. Okay. That's why it's considered as variable over here. But because the outcome is actually changes all the time. Okay, it can be changing from one to another outcome. So that's why it's considered random variable. Random variable. Okay, it can be real value. Okay, it must be real value, but it can be integer. It can be like decimal points. That's the reason why your outcome can be 1, 2, 3, or can be 3.2, 1, 3, 7, 6, 8, and so on. Okay, and there are two different range, two clear range. I wouldn't say range, forms okay, using the word forms of random variables over here, including discrete and also continuous. For you to easily differentiate these two, discrete, you have a finite or countable infinite. Means that whenever you are actually having a dice roll, you're actually having a finite outcome, which is maybe 1, 2, 3, 4, 5, 6. Countable infinite or infinite. Okay, sometimes it's infinite, sometimes infinite, but countable infinite. How are you able to define this? In general, we know that it's actually infinite long. Okay, but you try to make it steps. You try to make a step in the sense that you're only collecting or you are only calculating that particular data at one point. So usually we use the word stepped. For example, if you are collecting data every day, okay, you're collecting data every day, and then you are trying to collect the data in terms of step values, okay, step values. So in for example, every 10 seconds, you collect one. And then another 10 seconds, you collect another one again. So your outcome is actually somehow countable, okay, in that particular 24 hours. Okay. How is it differentiate between countably infinite and uncountably infinite is whenever you have uncountably infinite, you are given a time range. Okay, for example, 24 hours, or maybe easier, I put in 60 minutes. Okay, 60 minutes within 1 hour. But you are capturing the data, or you are actually calculating or measuring the variables, and potential outcome of the variables, in a continuous manner where you can accept every single variable inside within the range given. Okay, like this one, countably infinite. Countably infinite is actually you actually fix the potential outcome that you actually get. Like between 24 hours, you don't really get like 12.5, 16.1, 2, 3, and so on. You maybe have 10, and then 20, and then 50, where you always have a step of 10. Okay, but uncountably infinite is actually you can get any kinds of data within that particular range given to you. Okay, that is the reason why this one you'll be able to know the size of the values. You can predefine the size of the values, like when you are creating arrays in your programming, you can predefine your size on your arrays. But this one, uncountably infinite, you will not be able to predefine your size because you basically have infinite possibility. Okay, so this is the two difference between discrete and continuous. Okay, this is a third go home work. What's the probability for the number for the first dice roll to be higher than the second dice roll? Okay, and then given that there are 50 students in the class, 30 of them are male, 20 of them are wearing spectacles, what's the potential range? So please try this one after we have discussed all this during the previous classes. Try to attempt this one, and then this is the third bring home task, okay, for you to try on. So in summary, we actually discussed all these 1, 2, 3, 4 concepts. Combination with repetition, we're going to discuss it again next week. And then we actually have addition. Okay, this one, I think you already got the answer. And the third one is actually try this. So that's all for the class for today. Again, if you have any questions, you put in the message. Maybe I try to check it now. If there are any messages that I can answer. Dollar3 is answering, right? So I think fine.
Yeah, so far, whatever that I can see, I was answering.
Okay.
Yeah.
Slide 15 is okay, right? Let me see.
Because you asking the topic on a particular topic, you're asking the multiplication or something. So the student has said it's in slide 15 or something.
Okay. So yeah. If you have further questions, right? If you have further questions, I would suggest you to use Microsoft Team Chat. Let me see. Am I able to go back to the Team Chat? Okay, it's either you want to ask in here, or you can actually ask private messages using the chat function inside the Microsoft Team. Not sure why I cannot go back to my. I cannot go back to my screen right now, but yeah, please try to use the chat function, because if you use the chat function over there, right, I can reply you much more faster rather than you wait from the messages over here. Because I understand if you ask from here, then we can actually know that you're asking for lecture 1, but it's actually easier to use a chat. Yes, this one, I will upload it. Somehow, once we have ended the session, right, because this is a recording session, Microsoft Team will take maybe around 10 to half an hour. I mean, the longest I took previously is half an hour. they will automatically upload it. Because from our side, we don't do anything at all. We didn't do anything at all. The Microsoft team will do the processing on the video recording upload. So once I've recorded it, then you definitely upload. And then, hi, can you upload this live solution? Yes, I will. Because again, I will actually, like for example, Friday, I will actually upload a version without solution. And then Monday after the class, and I will do some fix as well, like what we have just now in the permutation and combination, I have some errors. Then I will upload the solution. But hopefully by the end of the day, I can't really do it right after that because I still have messages to answer. So I will upload this one. I will actually try to name it differently. Okay. And then, George, can we get the name list? What kind of name list you want? I don't really get you. Can you unmute yourself and ask again? I'm not sure what name list are you referring to. Yongming, can you unmute yourself and ask me? Yongming, are you here? Yongming? We need the name list to form team. Name list of students. Oh, okay. Okay. I think you can. We can do this when we actually have the tutorial class, because for me, right, for my classes, right, I will actually create another set of Microsoft team just for the tutorial. If you are from tutorial 1 and tutorial 2, then you know just from the team itself, and then from there you'll be able to see your participants. Okay. Right now you won't be able to see your participants because again, your tutorial not even started yet. But I believe you have some peers around that you actually can ask around, starting to ask around right now. Because there's actually one more rules over here is you can't cross group. If you are from group 1, you need to find your group members from group 1. You can't have students from group, and your members is from group 1, group 2, group 3, and so on. Okay, so it's better for you to start finding members when your tutorial starts, okay? But I will create it. I will create the groups by Wednesday. Okay.
Dr. Ho?
Yeah, sure.
You're creating the tutorial groups in Spectrum, is it? By groups?
I will also create the groups in Spectrum because that one is for them to submit the group project.
Okay.
But I will need to, because in my cases, I will also create one for the tutorial as well.
Okay, all right.
Yeah.
Because now we have group 1, 2, 6, and 7, correct? In this class.
Yeah.
Okay. So my group will be
Your group is 6 and 7, but the thing is, whenever we are delivering the tutorial, we are using the channel on this particular general channel. But when we are discussing about group projects and so on, I will need to let my students know that okay, you are from this group. And then you actually divide it into 5 to 6 in a group, what's your title and so on. I will need to discuss in that particular team as well. So this is my plan, but I'm not sure about your plan because you can use different ways.
Okay,
really,
because because my students are here, right? Group 6 and 7.
Yes,
okay, so if you are 6 and 7 tutorial, you're here. I will usually create a WhatsApp group actually for my tutorial group. So once I create that, usually I will have an invitation for particular group. So most probably I will do that in Spectrum. All right. So Dr. Ho, we can use Spectrum, right, to connect our group students. Okay.
In terms of evaluation, I think it's free for every single tutor to decide. Yeah. So I don't really restrict. Yes.
All right.
Just that.
Okay. So I just wanted to tell that group 6 and 7, check the Spectrum. I will post there if any information on how we will communicate further.
Okay. Things will be updated around Wednesday. Then you know.
Okay.
Yeah. And then continue. Wait. What was the name? There are a lot of different questions. The slide we get the name list. We have reference book. The reference book you can check the course information. There's actually a list of reference book over there. Then you can refer there. Okay. Can I know when the tutorial question will be uploaded? Wednesday. Wednesday, the tutorial one will be uploaded, and then you have 1 week to attend, and then next week onwards, and then next week we'll be discussing on tutorial 1. Okay. Then we name list, ask for team formation, name list, group project. Okay. Do we need to use IBM SPSS? No. SPSS, the SPSS will only be used starting around week 6 or week 7. I can't recall. I think it's week 7, but you can double check on the course information. Okay, because the front part for the first 6 weeks, I believe. Okay, first 6 weeks is actually probability and also intro to statistics. Then 7th week onwards, okay, 7th week onwards will be on the SPSS part. Does that mean there's no tutorial class this week? Yes. I actually mentioned this in the introduction of the course. This week there's no tutorial class, but you should start to attempt your tutorial, and also there's an online, we put it as an online forum. So you have any questions you can ask in your Microsoft Teams chats, or if you want to ask in Spectrum chats, and so on. Okay, but we don't really have a tutorial class for this particular week because it's the first week. I just deliver the lecture. You want to do the tutorial directly? I don't think it's I don't think you have enough time lah. Okay. So any questions else? Any questions? If no, then yeah, 10:50. I think the time is just nice. Then we'll end the recording over here. 5, 4, 3, 2, 1. Okay, thank you. Okay, so that's all for today. I know there's a bit confusion here and there, so also I will need to go and check my system as well, whether there's still students joining the group or not. So hopefully next week will be much more better. So see you all next week. And then remember the week Wednesday tutorial that will be going to be released.